Welcome, everyone. Today, we are stepping into the future of artificial intelligence. We are moving beyond simple chat windows and entering the dawn of the agentic era. Let's get started. Let's define what we mean by agentic AI. For the past few years, we've been fascinated by generative AI chatbots that generate text or images based on our precise prompts. But traditional AI is essentially all talk. It waits for you to tell it exactly what to do. Agentic AI, on the other hand, is all action. It's an AI that doesn't just respond to commands at every step. It can take a high-level goal, reason about how to achieve it, make a plan, and execute it autonomously. This represents a monumental leap. We are transitioning from prompt engineering, where we micromanage the AI's output, to directing autonomous systems that can navigate complex, changing environments on their own. Take a look at this diagram comparing the two paradigms. On the top, the traditional generative AI flow is linear and reactive. You provide a prompt, the LLM processes it, and you get a one-shot response. It stops there. On the bottom, the agentic AI system is cyclical and proactive. It starts with a broad goal. The AI agent enters a continuous loop of planning, acting by using tools and reflecting on the results. If a step fails, the agent adapts and loops back until the final outcome is achieved. Why do we need to move beyond prompt engineering? The answer lies in the limitations of static large language models. When you use a standard LLM, you are interacting with a static predictor. It generates the next most likely token based on its training data, but it cannot update its knowledge or interact with the world. Furthermore, standard prompt interactions are stateless. They have no memory. Researchers have also pointed out the illusion of thinking. LLMs mimic reasoning through pattern recognition but struggle to adapt when problems become highly complex. To solve real-world problems, we need systems that can actively gather fresh data, remember past failures, and execute actions which prompt engineering alone simply cannot provide. This visual breaks down the why. On the left, we see the limits of pure prompt engineering. It's stateless, locked into past training data, and incapable of executing actions. On the right, we see how agentic solutions overcome these hurdles. By introducing persistent memory, access to live tools like APIs and web search, and iterative execution, the AI breaks free from the chat box and becomes an active participant in your workflow. Let's dive into the basics of how an agentic AI is actually built. The architecture relies on four foundational pillars. First, the brain, which is the large language model itself, providing the generative and reasoning power. Second is memory. An agent needs short-term memory to track its current process, and long-term memory, often powered by vector databases, to recall past interactions. Third is the planning engine, which gives the agent the ability to take a massive, ambiguous goal and break it down into a sequence of actionable subtasks. Finally, we have the tools or action space. This is what gives the agent its hands the ability to search the web, run a Python script, or query your company's database. If you look at the diagram, the LLM core engine sits right in the center as the orchestrator. Notice how it forms a cohesive ecosystem with memory, planning, and tools. They don't just talk to the LLM, they inform each other. The memory feeds the planning module. The plan dictates which tools to use, and the output from those tools flows back into memory to inform the next cycle. It's a continuous, self-sustaining cognitive loop. To understand how agents operate, we need to understand state. The first step in turning an LLM into an agent is making it stateful. Think of a state machine, a computational model that exists in one specific mode at a time and transitions based on events. We use finite state machines, or FSMs, to break a task down. Instead of a single prompt asking for a blog post, an FSM moves the agent through distinct states: ideation, drafting, and editing. As things get more complex, we use hierarchical state machines, or HSMs. This allows us to nest substates inside a superstate, meaning we can apply global rules, like budget limits or safety guardrails, across the entire workflow, keeping the agent reliable and controlled. Here's a simplified hierarchical state machine. The outer box is our working superstate. Inside it, the agent loops between three substates: plan, act, and reflect. This is the iterative heartbeat of the agent. The beauty of this structure is the superstate. Notice the safety guard arrow pointing to end. Because these substates are nested, a global policy can instantly halt the entire process if a budget is exceeded or a safety parameter is breached, without needing to code that rule into every single substate. Now, for a deep dive into the operational core of most modern agents, the React framework. React stands for reasoning and acting. An agent that only reasons never impacts the real world, and an agent that only acts without reasoning cannot learn from its mistakes. React combines both. The agent generates a thought about what to do next, executes an action by calling a tool, and then receives an observation from the environment. Crucially, the agent's reasoning trace is folded back into its memory. It remembers not just what it did, but why it did it. This recursive structure grounds the AI, drastically reducing hallucinations because the agent relies on concrete observations rather than guessing. Let's trace the React loop on the screen. It begins with the user request, which triggers an internal thought. The thought dictates an action, such as querying a database. The database returns an observation. Here's the critical decision point. If the observation fulfills the goal, the agent outputs the final answer. If the data is incomplete, it loops back, generating a new thought based on the new evidence. This is exactly how human problem-solving works. As we embrace agentic AI, our skills must evolve from prompt engineering to context engineering. Prompt engineering is like giving an order to a brilliant consultant for a one-off task. Context engineering is like hiring, onboarding, and equipping a full-time employee. You aren't just writing a query, you are designing the environment the AI lives in. This involves integrating retrieval-augmented generation, setting up memory banks, and defining tool access. Prompt engineering doesn't disappear, but it becomes a subset of context engineering. Your prompts now serve as the foundational system instructions defining the agent's persona, its ethical boundaries, and the rules of engagement within its engineered context. This diagram illustrates the hierarchy. Context engineering is the overarching environment encompassing memory systems, tool orchestration, and knowledge bases. Notice how prompt engineering sits inside this environment. It is the specific tool we use to define the agent's persona and rules, but it is the combination of all these elements flowing into the AI agent that gives it true capability. We are building a workspace, not just writing a command. Just as a human worker eventually hits a limit on what they can do alone, a single AI agent can only handle so much complexity. The deep dive solution is multi-agent systems, or MAS. By dividing labor, we increase reliability and capability. There are a few ways to structure this. First is the supervisor architecture, where one manager agent breaks down a task and delegates it to specialized workers like a researcher agent and a writer agent. For massive tasks, we use hierarchical teams, essentially an entire corporate structure of agents. Finally, we have swarm intelligence, a decentralized model where agents dynamically hand off work to peers based on who is best suited for the immediate task, mimicking nature's collective intelligence. Observe the supervisor architecture in action. The user request hits the supervisor agent. The supervisor doesn't do the heavy lifting. It delegates. It sends research tasks to the researcher, coding tasks to the coder, and validation to the reviewer. The specialized agents return their work to the supervisor, who synthesizes the final output. This separation of concerns ensures higher accuracy and prevents a single LLM from losing context. We must conclude with the most important aspect of agentic AI, safety and governance. We are building orchestrated autonomy, not sci-fi free will. Agents operate within strict engineered boundaries. We must be wary of the lethal trifecta, untrusted inputs combined with sensitive data and tools that can export that data. To mitigate this, we implement human-in-the-loop, or HITL, workflows. This means inserting approval gates. Before an agent executes a high-stakes action, like transferring money or sending a client email, it pauses, presents its plan, and waits for a human to click approve or reject. By maintaining strict traceability and human oversight, we harness the massive productivity of agents while keeping our systems secure and aligned. This final flowchart outlines the human-in-the-loop safety mechanism. When an agent drafts a plan, the system assesses the risk. If it's a low-risk, routine task, it executes automatically. But if the risk is high, the flow is routed to a human approval gate. The human can approve the action or reject and edit it, which forces the agent to revise its plan. This ensures that you always remain the ultimate decision-maker in the agentic workflow.